Hey everybody, this is what we call in science my freezer. I just poured out some water to make ice cubes. Do you know that when you freeze water to become ice, that actually is a process that releases heat? That's a process that's called exothermic. Now don't confuse it with the fact that ice freezes at a very low temperature, but when it does, it releases heat. And you know who knows that? Orange farmers. And I'm not an orange farmer, but I am a guy who's going to talk to you about exothermic and endothermic processes and enthalpy. Let's do it. It'll be cool. Well, howdy everybody, howdy, Mike here. We're going to talk today about heat, energy, some more, specifically enthalpy. Now, enthalpy is a little bit more specific than heat. It's heat transfer with no change in pressure. Now, what does that mean? That means that we're not going to be pushing or pulling on the system. And if you've ever kind of expanded a gas or seen it compress, and you'll notice that sometimes you can change the temperature and what they call the internal energy of a system just by pushing on a piston and doing work on it. And so we're gonna limit that variable to be constant so that we're not going to be doing any of that. And we're just going to talk about heat transfer due to a process or a chemical reaction. So there's two scenarios, my friends. Heat can go in or heat can go out, and enthalpy if it's heat at constant pressure. So once again, we keep track of what happens to the system, and everything else in the universe is the surroundings. So if heat flows out of the system, final minus initial, heat final minus heat initial should be a negative value. Everything delta is final minus initial. And so that is a thing we call outgoing heat thermic, exothermic process, this outward arrow here. That would be this. What's the other one? Well, the other scenario would be, sorry, that's supposed to be a negative sign. The other scenario would be that somehow the system gained heat from the surroundings, so the amount of heat final would be greater than the amount of heat initial, and that would be a positive value. And we call those processes or reactions endothermic. If you need a little hint, do you know an extrovert? Extrovert, X means outgoing, exoskeleton, skeleton on the outside, endoskeleton, skeleton on the inside. So outward, inward are those what those prefixes sort of entail. So let's talk, before we talk about chemical reactions, let's talk about just something you're probably pretty familiar with. Let's talk about what we're going to do in my freezer making ice cubes. And now if I go and take all the different phases of water, I can kind of arrange them in terms of energy. Now you know that water molecules that are gas have the most energy out of all the three phases because they're moving around randomly. They've somehow acquired a lot of energy. And then liquid would be a little bit less in energy, and then solid, of course, you'd have to take the energy out. And so what happens, I think the easiest thing to visualize would be, I'm going to boil a pot of spaghetti, and I would have to go turn my stove on and put energy in to the system to make that happen. Or I'm going to take an ice cube out of the freezer, and I don't have to really do anything, but the surrounding room temperature energy would do that. And so going this way, this would be endothermic. All right, these processes going up would be endothermic. And these processes going down would lose energy, and that would go to the surroundings. That's exothermic. Now, for water and all things, these have different names, and we use the term delta H still. This would be delta H of vaporization. By the way, if it was water, it would be 44 kilojoules per mole. I'm going to put plus or minus because we don't know which way we're going. And so this is why your sweat works. If you have to, you know, if you're going to go out for exercise and you go and your sweat evaporates, it's going to take that amount. And then, by the way, for water, that's a very big amount of energy. It's going to have to take, you're the surroundings, and now you're the one supplying the heat that would make this liquid vaporize. So sometimes they give it, you know, little subscripts like that, delta H of vaporization. It would be positive 44 kilojoules going up to make the liquid vaporize, and it would be negative coming back down. And that's why steam can really burn you. Not only is steam hot, more than 100 degrees Celsius, but when it lands on something, it's going to have this heat of vaporization come out of it into the surroundings. So double whammy there. Same thing with making an ice cube, and if I could fit this in perspective, this particular energy is much smaller, but that would be called delta H of fusion. So one interesting thing that's very nice about the universe, I forget what delta H of fusion is, it's smaller, way smaller than 44 kilojoules, is that if you know the delta H of the process going one way, then the opposite way is just the negative of that, or the opposite sign. And so this is 44 kilojoules per mole going either way. And this kind of, you got to watch out, because you know, when I was talking about the ice cubes, if you're an orange farmer, here's an orange, and there's a frost coming, right? There's an orange, and then I got to be factually correct. You know, make a little leaf there or something like, I don't know. So what's an orange farmer going to do? Frost is coming. Okay, spray it with a fine mist of water. And then if there's a hard freeze overnight, delta H of fusion would be liberated to the surroundings, which means the air that way, but also into the orange the other way. And then, interesting thing, ice is actually also a pretty good insulator. So, and then that would not work permanently forever, but that might get the orange through the night, and the orange farmer might not lose his or her crop. So interesting kind of applications of these things. And what I want to do next is not talk about phase changes as much. I want to talk about how we take care of figuring out the delta H of a chemical reaction. So we'll talk about that next. All right, so next we're going to talk about like making and breaking bonds instead of just changing phases. And in order to do that, we need to know how much stability compounds involved, or elements involved in a chemical reaction, how much stability they have. So we have this measure called enthalpy of formation, specifically standard enthalpy of formation. So you got this little degree symbol here, and that's put on anything that's standard. Standard conditions. What are standard conditions? Well, we're not going to do anything like heat something up, anything more. It's an apples to apples comparison. I didn't want to say oranges because I just did enough with oranges. So 25 degrees C, 1 mole, 1 atmosphere pressure if it's a gas. Basically, we don't want to compare things at different temperatures. They'd have different amount of heat available to them. Formation means if we were to take something and form it from its elements. Now, interesting thing, elements, we all know the periodic table of the elements, and we know that some of the nonmetals have different forms of the elements. And so what we have is the stable form of an element would be no change. Forming it from the elements would be nothing, right? So I go and take oxygen, make oxygen, O2 from O2. So what we do is we have sort of a ground level reference point to figure out, you know, where all these compounds are relative to their elements. And that means the more negative the delta H, the more stable the compound. So if something is a great deal more stable than its elements and you form that compound, a good example would be water. So water is more stable than hydrogen and oxygen, the elements. And that's why water happens. That's why water occurs. And so you would find a negative value. But that doesn't mean that a compound can't happen if it isn't more stable than its elements. And so some of them are positive, some are negative. So here's a few examples, like oxygen, 0 kilojoules per mole because it's an element. Magnesium oxide. Now, if you take magnesium and you put it to oxygen, it will go through this very, very sort of dramatic reaction, which is extremely exothermic, and you'll make magnesium oxide, which is much more stable than the elements it came from, or that would not have happened, that reaction. So it's kind of downhill in energy, right? And so magnesium oxide has a very large delta H of formation, and delta H of formation is usually in kilojoules per mole. Here's acetylene. Acetylene is a pretty unstable compound. If you put a match to it, it'll burn very readily. And so you'll see that that's positive 226 kilojoules per mole, which means it's more stable than the carbon and hydrogen from which it came. And so here, my friends, is a table of enthalpy of formation of the elements. All right, no, not just the elements. No, not the elements at all. Enthalpy of formation from its elements. And on this particular table, I don't have any elements, so it's understood that there's 0. So you'll notice here over where oxygen is. Let's look at oxygen. You will notice that there's 2 values peeking at you. Oxygen, monoatomic oxygen, and then ozone, which is, you know, pretty positive. And so let's go peek around here. Carbon. Carbon. The stable form of carbon isn't on there, it's a 0. Stable form of carbon's graphite. Diamond is higher energy than that because it needs a whole bunch of pressure to make a diamond. And so what we're going to do next is we're going to do a chemical reaction and calculate a delta H of the reaction. But you just look them up on the table and we do final minus initial. If the stuff we made in the products is more stable than we started with, then you have an exothermic reaction. It's like pushing a boulder down a hill. If the stuff you made in the products is less stable than what you started with, then you have a positive or endothermic process, kind of like pushing a boulder up a hill, depending on, you know, it might not be a boulder if it's not very positive. Might be like pushing a big rock or something. So let's do an example. And by the way, if you have a different textbook, and this one is, you know, this one's meant to fit on 1 page. It does not have every single compound in the world on there. So you might find that you have one that's 8 pages long. I'm using this one that's just 1 pager, just to make things a little simple. So let's talk about doing an example of a delta H of a chemical reaction next. All right, here we go. The rubber is meeting the road, and we're going to have another video next time where we do this a whole bunch more. But what we're doing now is I'm going to take the example of carbon monoxide adding another oxygen atom by reacting with a 1/2 mole of oxygen to make carbon dioxide. And anything you do, it's always final minus initial. Products, delta anything is final minus initial. I should take a moment to mention a cautionary tale here. When we write a chemical reaction, its initial goes to make final. So everything kind of gets reversed. What was on the left was on the right. And what I'm going to do here is I'm going to go ahead and pull off some of the values of everything. And so I'll first write down symbolically what we're going to do. I took it easy. I got some pretty simple coefficients here. And by the way, that gizmo right there, that's a sigma. That means the sum of the delta HFs of the products minus the sum of the delta HFs of the reactants. So this would be, now watch out, that's on the product side. So this would be the 1 times the delta HF of CO2. That's final. Minus the delta HF of CO plus 1/2, because it's done per mole, the delta HF of O2. Now, here's a wonderful thing. Simplification. I balanced that reaction. I didn't even have to balance it with a 1/2 because the delta HF of O2 is 0 because it's an element. Formation of the of it from its elements is just it, so that's a 0. So whenever you see an element, you don't have to stress out too much about it. But I do have to go look up the delta HF of CO2, which is right there, minus 393.509. Oh, and then right next to it, its neighbor is carbon monoxide. So watch out, you don't, this is kind of like energy accounting here. So this would be, and you got negative signs. A lot of compounds have negative delta HS, so you got to kind of be careful. Minus 393.509. I'll leave the units off. It's all in kilojoules per mole. Almost any table you'll see, it'll tell you it's kilojoules per mole. Minus negative 110.525. Of course, that's a double negative, so that would be like plus a positive. And so minus 393 plus 110.525. This would be delta H. Well, we could just call it a reaction. It's going to be minus 282. And by the way, there's no sig figs here. This is all theoretical. It's all out of a table. Kilojoules per mole. So what does that mean? What's a mole of carbon monoxide? 28 grams. If I took 28 grams of carbon monoxide, react it with enough oxygen to make CO2, I would have an exothermic process. It would liberate heat to the tune of minus 282.984 kilojoules per mole. And that would actually pass heat from, because of the negative sign, the systems to the surroundings. A lot of things that are oxidation are exothermic, but then you'd say, okay, now what does that really mean? And then this is what I want you to do, folks. I want you to not just think of these as numbers, but it's telling you what the universe wants to do. That means that product of CO2 is a little bit more stable than carbon monoxide, and thank goodness for that, right? I mean, we have carbon monoxide detectors in our house, and sometimes carbon monoxide is produced when we don't add enough oxygens to carbon-based fuels. But carbon dioxide's a little bit more stable than carbon monoxide. So the universe kind of it's kind of rooting for this reaction to happen. because things that are more stable tend to occur more easily. And so that's the thing that you kind of get away from a delta H. Or, you know, if something is, you're making something more stable out of something less stable, you usually got a delta H negative. And so more on this next time, because we're just getting into the meat of it, but we're going to be using this table a whole lot more. Look at all those things on there. I'll pick out some wonderful examples, and we'll go forward and backwards and sideways. So we'll see you then, and take care.